Hello everyone, it's Ali from Swiss Course. Welcome back for another math adventure. Today we're delving into the world of radians. We'll cover everything you need to know about radians. So grab your pencils, get ready to make some notes, and let's get started. Imagine there is an object moving along the circumference of a circle with a radius of 100 meters. The question is, how far will the object move if it travels 180 degrees from point A to B? As you might agree, it covers half the circumference or the perimeter of the circle. Given that the radius is 100 meters, the full circumference is 200 pi meters. So half of that is 100 pi meters, which is approximately 314 meters. Therefore, we can say the length of the curve AB is approximately 314 meters, which is the distance traveled by the object. So our object travels approximately 340 meters by passing 180 degrees. Now let's imagine we don't have the exact length of the radius. In other words, our object is traveling on a circle where the radius is not measured. In that case, by replacing 100 meters with r as the radius of any circle, our object will travel pi r to pass half the perimeter of any circle. In other words, in any circle, the length of a half-circle curve on the perimeter divided by the radius equals a constant value which is called pi. Attention! We've just established that the ratio of the length of a half circle to its corresponding radius is constant. However, this does not mean that the ratio of any curve to its radius is always constant. For example, as you have seen right now, a 180-degree arc on a circle with a 100-meter radius has a length of approximately 314 meters. Using simple proportionality, we can calculate that a curve of 100 meters on the same 100-meter radius circle corresponds to a central angle of approximately 57 degrees. In conclusion, when the length of a curve is equal to the length of its corresponding radius, the resulting central angle is always a constant value, approximately 57 degrees. In other words, in any circle, regardless of its radius, when the length of an arc is equal to the length of the radius, the central angle formed is approximately 57 degrees. Conversely, a central angle of 57 degrees has an arc length equal to the radius. This is how we define another unit for measuring angles, called a radian. A radian is the measure of an angle whose corresponding arc length is equal to the radius. Therefore, 1 radian is always approximately equal to 57 degrees. Based on this definition, you now understand that if an object moves 1 radian around the circumference of a circle, the distance traveled is equal to the radius of the circle. If it moves 2 radians, the distance traveled is twice that radius or equal to the diameter of the circle. Finally, if it moves pi radians, it has traveled halfway around that circle. It's important not to confuse the length of the arc AC with the length of the diameter. The diameter is 2r or twice the radius, but it does not correspond to 2 radians. 2 radians is always less than pi radians, which is the length of the arc forming a semicircle. Now let's work through this exercise to solidify your understanding of radians. Please note that angles are expressed in degrees when accompanied by the degree symbol, and in radians when no symbol is present, as demonstrated in this exercise. As you can see, the ratio of the arc length to the radius in any circle is, in fact, the measure of the angle theta in radians. In this part, let's explore the relationship between the length of an arc and its corresponding central angle. To do this, consider a circle with center O and radius R. Let's call the central angle theta. If theta measures 1 radian, the arc length is equal to the radius. If theta measures 2 radians, the arc length is twice the radius, and so on. Therefore, the measure of any central angle in radians is equal to the ratio of the arc length to the radius. Conversely, the arc length is equal to the product of the radius and the central angle in radians. And in this part, we want to see how to convert between radians and degrees. There is a simple method to remember. To convert radians to degrees, replace pi with 180 degrees. And to convert degrees to radians, it's enough to replace that degree symbol with pi over 180. First, pause the video and carefully read the exercise. To solve this problem, we'll start by converting 135 degrees to radians. Which is 3 pi over 4. Next, we'll calculate the length of the inner curve. Which is approximately 235.5 meters. Then we'll find the length of the outer curve. Which is about 254.3 meters. For the second part, we want the outer runner to curve the same distance as the inner runner, or 75 pi meters. This corresponds to an angle of 126.5 degrees. Therefore, the inner runner needs to start approximately 8.5 degrees closer to the finish line for a fair race. Pulleys connected by a belt provide a great example of radians in action. Let's convert the larger pulley's rotation from degrees to radians. (270 degrees equals 3 pi over 2 radians. Next, we'll find the arc length the larger pulley covers. 12 units or 12 centimeters multiplied by 3 pi over 2 radians equals 18 pi units. Since the belt connects the pulleys, the smaller pulley also travels 18 pi units. And finally, to determine the smaller pulley's rotation in degrees, we divide the arc length by its radius. Converting back to degrees, we get 1080 degrees. This slide shows common angles in both degrees and radians. To memorize these, focus on two key conversions: pi over 6 equals 30 degrees and pi over 4 equals 45 degrees. The other angles are multiples of these. Let's also use this slide to review the trigonometric ratios you learned in previous videos. So the second multiple of 30 degrees is 60 degrees, which is equal to 2 times pi over 6, resulting in pi over 3. And its third multiple is 3 times pi over 6, which equals pi over 2 or 90 degrees. It's the same pattern for 45 degrees or pi fourth. Multiplying it by 2 gives us the second multiple, which is pi half or 90 degrees. Look at these pizzas. Any slice of these pizzas is called a circular sector or simply a sector. In this section, we learn first how to calculate the area of a sector. So to be more precise, we are about to calculate the area of the shaded region. We know that the area of a circle is calculated by pi r squared. So when the angle is a full circle or 360 degrees, the area equals pi r squared. By using a simple proportion, we can calculate the area of a sector when our central angle equals theta. So the area of a sector is equal to half the radius squared multiplied by the central angle. Now for the most interesting part of this video, we'll look at how to calculate the area of a cone produced by rolling a sector of a circle. First, let's see how a sector becomes a cone in 3 steps. When we roll up a sector, the radius of the circle it was cut from becomes the slant height. It's the same measurement but with a different name. To avoid confusion, I'll call the base radius of the cone capital R and the radius of the sector lowercase r. Now let's write down our first equation. The circumference of the cone's base is 2 pi r, just like any circle. Next, let's call the arc length of the sector I and write down the second equation. As the arc length equals the circumference of the cone's base, we can replace I with 2 pi r in the second equation. Don't forget to change the radius symbol from lowercase r to L, as they represent the same value. We already know the area of a sector is calculated by theta r squared over 2. Let's substitute the formula we just found for theta into this equation. Now let's see how to calculate the area of a cone made from any circular sector. One more time, the circumference of the cone's base is equal to the arc length of the sector it was made from. And essentially, calculating the circumference of the cone is the same as calculating the area of the sector.